Yay!
Yay! Let's look at how the current behaves over time in a circuit with capacitors in it. Let's suppose I've got a couple of light bulbs, like a 60 ohm and a 20 ohm light bulb, and I've got a switch, and I put into this little circuit two capacitors. One is 10 microfarads, one's 20 microfarads, and let's suppose they're both charged up with 24 volts initially. So I put them in here, and then suppose I close the switch S. So what's going to happen is those capacitors are in parallel with each other, so they're both going to supply the 24 volts. And they're going to light up these light bulbs because since we close the switch, we're sort of connecting the positive and negative terminals, and the current can flow. So let's see, initially, let's see, what is... initial current. Sometimes that's called I naught. Because remember how the current behaves. The idea is that the current at some time is just going to be the initial current times e to the minus t over RC, right? It's an exponential decay. So if you graph it or something, right? If this is the current and then this is the time, you start off up here at I naught, and then the current decays over time. It gets smaller because as the capacitors discharge, the current goes down. Okay, so what is that initial current I naught? Well, the initial current is just going to be the initial voltage over the equivalent resistance for the whole circuit, right? Because that's what's limiting the capacitor's ability to discharge immediately. So this is just going to be 24 divided by what's the equivalent resistance of that whole circuit? Well, you just add together the resistors because they're in series with each other. 60 plus 20 is 80. So 24 over 80, and so this is just going to be 0.3 amps. Right, is going to be running through the circuit initially. That's sort of where we start off. And then what happens? The whole behavior of the circuit is governed by this, that combination RC in these circuits. And RC is called the time constant. And here, the time constant is just going to be the equivalent resistance. That's going to be EQ, right? It's going to be REQ, the resistance for the whole circuit times the capacitance for the whole circuit. And that combination of things, it's not obvious, but that combination of things has units of seconds. It kind of has to, because look up there in the exponential. The exponential has to be unitless, so if there's a t on the top in seconds, RC, the combination has to have units of seconds on the bottom. But probably the first time you saw RC together, it wasn't immediately obvious that you were like, oh, that's got units of seconds, right? You have to kind of, if you put the definitions for the units in there, it's going to work out that way. But that's kind of cool. So REQ, CEQ. Okay, so that what's that going to be here? That's going to be 80. The resistors in series just add together. So 80 times, and then the capacitors in parallel just add together. So that's going to be 80 times 30. And so that's just going to be, 30 microfarads, right? And so this is just going to be 2.4 milliseconds. I think I got milliseconds. There we go. So this is the time constant for the circuit. What does the time constant mean? That means after RC seconds. So suppose t is equal, t on the top of that exponential thing, suppose t is equal to RC, right? Then the current at RC seconds is just going to be I naught times e to the minus 1, right? Because t is just equal to RC. e to the minus 1, that's just 1 over e. E is just a number. It's kind of like pi, except it's a different number, 2.7818, whatever. But 1 over e is, what is it, like 0.37, something like this. It's going to be about 0.37 on, it's about a third. Just in the back of your head, you can just think of 1 over e as about a third. That'll become useful as you go along. It's sort of called 1e folding. So after that amount of time, the current has decreased to about a third of its initial value. I don't know, maybe that's about right here. So that's RC in seconds, and this would be I at RC. So after one time constant goes by, you know that the current has gone down by roughly a third. The reason it's called the time constant is that it's just a useful thing that you know about a circuit because you've built it. You know what the resistance is, you know what the capacitance is. So you can compute immediately this sort of time scale, that on this time scale, the current is going to decrease by this much. If you wait another time constant, then the current is going to go down by e to the minus 2, another factor of almost 3. And by the way, what does that mean for the light bulbs? If the current goes down by a third, then the light bulbs are going to get dimmer, right? But how much dimmer? Not a third, because remember, the brightness of the light bulb is related to how much power it generates, how much power it dissipates, and that's I squared times R. So if the current goes down by a third, then it's going to get approximately about 1/9 as bright. So almost a factor of 10 is the brightness diminishing. There we go. So this is going to be about 0.11 amps, something like that. So at any time in the future, you can figure out what the current is based on the general formula up here. But just the rule of thumb is, if you know what the time constant is, just RC for the circuit. So you can sort of estimate it quickly as you go along. So that's how the current in these circuits with capacitors behave. They decay over time.